Hello, everyone, and welcome to another ANT podcast. I'm Carrie Cole, editor of Materials Performance Magazine, and this episode is part of the special series spotlighting the winners of the 2025 Materials Performance Innovation Awards, celebrating cutting-edge technologies that are driving progress in corrosion control and protective materials. Today, we're highlighting one of this year's award-winning innovations in the corrosion control cathodic protection category, closed-loop smart cathodic protection technology, developed by researchers at the Deakin University School of Engineering in Australia. This technology uses a specially designed corrosion probe and real-time monitoring to smartly adjust cathodic protection levels, making it possible to tackle complex, localized corrosion problems more effectively, even under disbonded coatings or in harsh environments. Joining us is Professor Mike Yongjun Tan, who led the development of this innovative system, to share how it works, what sets it apart, and how it could shape the future of corrosion prevention across energy and infrastructure. Professor Tan, thank you for joining us, and congratulations on the award.
Thank you very much, Carrie. Thank you for the invitation. And that is a wonderful honor, and we're really proud of the award. And when we got the news, our innovation has been awarded the award. Our team was extremely happy, and we're proud. And also our collaborators, our Future Fuel Cooperative Research Center in Australia and the university colleagues, they know this. They are, very happy and congratulate us. And also another thing we come to our mind is we are very thankful to AMPP, to the Materials Performance Magazine. That is such a wonderful, support and recognition of our research.
So, for our listeners who might not be familiar with cathodic protection systems, can you give us a brief overview of how cathodic protection works and how your system is different from conventional CP methods?
Okay, cathodic protection is very important. It's a very important technology for protecting infrastructures and many infrastructures underground and in the ocean. Cathodic protection is one of the most important technology for protection. And we have standards, industry, we have standards to control the potential, cathodic protection potential levels, which based on the standard, we are quite certain the structure is protected. But the existing cathodic protection technology has one bigger limitation, which is the cathodic protection potential is more or less fixed. Okay, then they are not able to reflect the changes of the corrosion mechanism, corrosion conditions, and the changes in the system. This is quite a big problem because a lot of incidents, a lot of damages to the infrastructure at the moment is due to a problem called localized corrosion, which is exactly due to this type of localized issues and the changes in environment. But the cathodic protection at the moment, it cannot adjust, cannot basically make changes based on the environment change and the mechanism change. For that reason, the cathodic protection can often have under protection or over protection. Under protection, we will have localized corrosion issues remaining, and all protection can have problems with issues like hydrogen embarrassment and coating disbondment, a number of issues. So our closed-loop cathodic protection technology is designed to try to address these issues. So this is the objective or the background of this technology.
I see. Thank you for explaining. And at the heart of your technology is a localized corrosion probe with an electrochemically integrated electrode array. What's unique about this probe design, and how does it help monitor and simulate localized corrosion in real time?
As I mentioned, the biggest problem, or I can say the major unsolved problem in corrosion science and engineering, I can say is the localized corrosion and its control. Because the localized corrosion, it happens into, like I say, in the crevices or in some way you don't see. And maybe the whole structure is protected by Cathodic protection and the coatings, and 99.5% of the surface, no problem, are perfect. But you just have a few locations because the environment at that location and the condition at that location is so different. Okay, and the corrosion happens just on that small locations. This small corrosion, even is the area is small, but the problem is big because you think about a oil gas pipeline, you only need to have one pinhole, okay, to damage your whole system. And a bigger structure, you have a small damage. That small damage can be the stress concentration point, can cause a fracture initiation, and the damage is initiated by this local damage. So that localized corrosion is a bigger problem. Okay, so to monitor this localized corrosion is a big challenge. If we look into the literature of corrosion science and engineering, traditional way of monitoring are basically more or less to detect general corrosion. Okay, the general environment corrosivity and this type of things. All these techniques are designed for that. So we have designed a probe. There's a big long story behind this development. But anyway, the probe is designed to be able to catch up look changes. Okay, to simulate a situation. For example, you have a problem with crevice corrosion. Okay, then we design the probe to simulate that crevice corrosion situation. If you have a corrosion and, for example, stray current corrosion, then we design a probe to simulate the situation and to catch up the worst case scenario condition and the other condition. Then we know what's happening, what is the worst happening. Then we are able to adjust Cathodic protection to overcome that. There is a good mechanism behind how that Cathodic protection adjustment can do that. Because Cathodic protection can not only adjust the potential, but also leading to chemistry changes. They leading to a high pH environment. If we push Cathodic protection temporarily, you can change the pH of that particular area of localized corrosion, then can mitigate and localized corrosion. That's the basic concept behind this technology.
Now, a key part of your innovation is its smart closed-loop function. How does the system automatically adjust CP current or potential based on the environment, and what kind of data does it rely on?
When I talk about the probe, the key component is the probe. Okay, the probe basically, as I said, we simulate a condition, localized corrosion happens. Okay, then we put this probe into the environment, at the same environment and the same condition as the structure, like a pipeline, for example. Okay, when the environment changes, for example, you get a rainfall, get a lot of water, takes oxygen into the soil, and then your corrosion initiates. Okay, localized corrosion initiates. Okay, then the probe can tell us corrosion is happening at a certain rates. Okay, in that case, this information, this data through the monitoring system, okay, automatically, identify the corrosion rates, the type of corrosion, then automatically feedback, okay, and automatically say, okay, you need to apply more CP for a period until this corrosion stops. Okay, so this is more like a data-driving Cathodic protection adjustment process. The data, the probe can get the data in situ pretty quickly. Okay, then generally with this data, we adjust the CP level, to stop corrosion, and then we retain this CP to the normal level. That's how the system works.
This September 8th through the 10th, all roads lead to Odessa, Texas for the AMPP Central Conference, where the future of corrosion and coatings comes to life. From AI-driven pipeline integrity and advanced cathodic protection monitoring to cutting-edge AC interference strategies, this is where innovation meets infrastructure. Dive into groundbreaking technical sessions tailored to the challenges of the central U.S. and the Permian Basin. Advanced registration is now open. Secure your spot today and save. Register now at ampp.org/central-conference.
Now, localized corrosion under disbonded coatings is a tough challenge, especially in underground or offshore environments. How has your technology performed in addressing these types of complex corrosion scenarios?
Yes. Okay. So this probe, okay, this electrochemical array probe is a general concept. Okay, in principle, it can be you can design many different type of probes to apply in different conditions. But one of the biggest problem in Australia gas industry is a problem called corrosion and disbonded coatings. We have working with this industry for a long time. Okay, so we have been, this is one of the issues that come to us to ask us to what to do with that, because this has been around for such a long time, and they tried all different methods. At the moment, what they do is has to use a inline inspection, very expensive inline inspection to detect the corrosion, and then identify areas of this localized corrosion and the disbonded coatings. And then they dig up and then they pay and they fix it. This is very, very expensive and very, very slow. And then they ask us, is any better solution to this problem? So, okay, then we have my colleague, Bob Valley. He's also listed as an inventor for this new technology. When he did his PhD with us at the university, he basically used this electrochemical array concept and make this surface to simulate a disbonded coating. Okay. Then we put this probe to the industry. Initially, we use that to simulate and to monitor this corrosion. And basically what we did was we make this probe and make a instrument. Then we put the probe next to the pipe, say half a meter away from the pipe, and the same condition, and connect to the CPE. And then we continue monitoring. Then we found actually this type of corrosion doesn't happen all the time. It's active only within a few periods in a year. That period is usually due to the climate, the weather changes, like say from the rainfall and then to dry season, the transition period. We find actually radioactive for this type of corrosion. And then we publish some papers explain why that's the case. So industry realized, okay, we don't really need to apply a lot of CPE for the whole year. The CPE is needed and need more during these active periods. Okay. And from that concept, then we say, okay, why not? Why not we actually use this data, this information to automatically drive the CPE adjustment? Okay. Then after that, we have made the prototypes, and then we installed these probes. At the moment, we have installed 2 major locations and 4 other locations in Australia, in Victoria and Melbourne, that area, and we continue testing for a number of years. Yeah, so is the way we try to address this problem, and industry is quite interested in that, because this corrosion problem is basically 90% of the corrosion-related pipeline issues is due to this corrosion problem. So the industry thinking if this technology can be applied, then they have a good potential to basically to extend the life of the pipeline, and potentially can save a lot of money. So because the pipelines can be extremely expensive. So this is a bit history of industry collaboration.
Interesting. Thank you for explaining that. Now, you've emphasized that this system avoids the problem of overprotection, which can actually damage coatings. So how does the system strike that balance, delivering enough protection without causing cathodic disbondment or other issues?
Good question. So as I mentioned before, Cathodic protection is good, but they can have a problem with underprotection or overprotection. For the pipeline, for the gas pipeline industry, overprotection means you apply too much Cathodic protection current. That way, of course, that can cause too much reactions. That reaction can actually produce a lot of hydroxy ions or H minus ions. We generate a high pH at the surface. That is high pH. If it is a reasonable pH value, that's fine because that can be useful because it can cause the surface preservation, which is protective. But if too much, they can cause coating disbond. It's called a cathodic disbondment of coatings. So this is a bigger problem, okay? Because the coating is the important part because majority of the surface needs to be cut by coatings. But that high pH can lead into the coating start to disbond. Of course, that loss protection. And also overprotection, is a cathodic, a lot of cathodic current in some situations can generate hydrogen. Hydrogen can be a part of the cathodic reaction. So the hydrogen can do two bad things. The one thing is they can actually get into the pipeline, cause a problem called embrittlement. They change the mechanical property of the pipeline, potentially can cause the pipeline lose their strength. Another problem is the hydrogen can actually push up the coatings, cause more disbondment. So all protection is not good. Okay, this is new technology. How we actually avoid this all protection? Because this monitoring, we can see corrosion happening. We can also see the cathodic current. Okay, if the cathodic current is too much, because if corrosion is almost gone, there's no more corrosion, you don't really need to push the cathodic current too much. So in that case, you can really reduce it. And we basically until the corrosion, you can see that if you look at some of our papers, we can see this is usually red color. If you don't see much, we industry Australia we set a limit of 0.1 millimeter per year, but actually we have a bit lower than that. So then we can reduce the cathodic protection level. Then we can avoid this overprotection. The same applies to the marine condition, offshore condition, and this we avoid this to happen.
Okay, thank you. So your prototype has been tested since 2021 on underground gas pipelines in Australia. What were some of the key takeaways from those field trials, and were there any surprising results?
Okay. Yes, and not because of the support of the industry, particularly in Australia, the APA Group and Gemini and a few companies, they give us a lot of support. To find a gas pipeline to test a new technology is not easy because, the safety regulations are lots of things, and they give us a lot of support. So we are able to install this, a few of their pipelines. The strategies, we put this technology on one section of the pipeline, and then we put a monitoring on another section of the pipeline. They keep a distance of 20 kilometers, and then we compare. We can say with this control and without the control, and then to see what happens. But a big challenge for this technology application or development is the industry. They want to see the end results. For example, after 10 years, and use inline inspection to see the difference. But for testing for 10 years is a long time. And then for that reason, we put some coupons. We also next to the pipe, but still take a time to actually visualize to see the difference. But in the lab, all the results, basically simply we say it's working. We have data, but the industry is still wanted to see the end results before they widely apply this technology. But anyway, that's the situation. And also the field trials, a lot of we are researchers in the uni. We did have some interesting experiences because some of the cables, some of the can be these animals or the ships kangaroos and can damage. This type of things can happen. But anyway, we sorted out, we improve, so we continue the testing. At the moment, we are making the equipment much smaller. We're collaborating with another Australian electronics company in Sydney. They make that for us. And we are going to install more, make this equipment truly environment proof and towards practical application. Yeah. So the results has been good. As I said, we have not tested many locations, but the location we have tested so far, the protection, we compare to the situation without protection, I can say the efficiency can be close to 90%. That's from that test results we reported in a paper in this year's AMPP conference.
Yes, I see. Thank you for explaining. Now, with the rise of renewable energy, we're seeing infrastructure move to more remote, complex environments like offshore wind and hydrogen pipelines. Why is localized corrosion control especially critical in these emerging sectors?
Okay, thank you for asking this. This is an issue actually I have been talking and thinking for the past few years. You know, the renewable energy is a big topic in Australia because of the government. We have set a target. Okay, we have wanted to get a 43% reduction in CO2 emission by the end of the decade. And then we work towards the 2050 to get a zero emission. These targets. Basically, our colleagues, they did some analysis. They say we need a lot more these structures, a lot more wind turbines in the ocean and solar farms. Generally, this are bigger infrastructures. They are huge, and also usually they are located in very remote locations. The environment can be quite complex. Okay, then the issue is the design life at the moment standard is like 25 years or something like that. But if you think about the difference between this renewable energy infrastructure and the traditional oil gas infrastructure, they are different. Okay, because renewable energy infrastructure, we need that forever. Okay, we really like to have them for a longer time, and the structures are so big. Okay, and if you say have to take it down and rebuild every 25 years, that's very difficult, and recycling is very difficult, and there is energy consumption and CO2 emissions. It can be issues, and it's not really sustainable. So we believe this important to make sure the main structures of these renewable energy systems last much longer. So we do think there's a good possibility, good opportunity to make that towards 100 years. Because it's possible because if you look at some of the bridges, okay, in Sydney, we have a Sydney Bridge is more than 100 years. It's still look good, it's still good. So what I say, if we design the structure properly and we maintain that properly, we do have a good opportunity to make that much longer, at least the main structure. But the biggest challenge for this type of structure is, as I say again, localized corrosion, localized damage. Usually, this type of big structures, the damage initiates from a local area. Okay, you can have a local damage, then you say under a big stress, that will be the cracking initiation point. I think we believe that is truly why this life is limited. And it's not because of the concrete cannot last long enough, or it's not because of material cannot last enough, just because the damage, especially local damage, needs to be controlled. So, but anyway, we would think that would be a biggest issue we have to solve. Okay, we have to address. Probably, in my point of view, that probably would be one of the biggest issues for the corrosion community in the future. Yeah, and how to address the issues with wind farms, solar farms, and the battery systems and pipeline systems. This would be big issues ahead. Yeah.
Well, 100 years would be an incredible accomplishment for sustainability. So, looking to the future, what's next for closed-loop CP technology? Do you have plans to expand its capabilities or integrate it with AI or something?
Yes, I think generally at the moment, we have got the Australian government support. Australia has a government program called Australia Economic Accelerator program, which basically identifies technologies developed in universities, okay, and try to promote or to develop into practical applications. Yeah. So at the moment, we are supported by a program. We are going for the next stage of this Australia Economic Accelerator program, and what we are looking for collaborators. Yeah. So truly, I believe this technology application, we need more collaboration globally, and especially I would really like the AMPP colleagues, the members. Yeah, maybe we can work together to test, to evaluate, and to use this technology. Okay, and of course the data, because this technology produces a lot of data. With the data, we would be able to integrate with AI. AI could, and also machine learning, or we give us a useful information for us to identify the what type of sensors we need to simulate what type of conditions and the location of sensor installation and a smarter control. I believe this will be one type of important data, because the data has come in situ, could be used more widely, and not only for the Cathodic protection, but also for coating maintenance. Okay, for example, this sensor can tell us the condition of the coating, local damage of the coating. So maybe we can make this coating maintenance and also say inhibitor application or maintenance program in general smarter. Okay, and more like a data-driving strategy for corrosion protection as a more like a direction. I think this would be a great opportunity.
And finally, for students or young engineers interested in corrosion science, what advice would you give to those hoping to create the next breakthrough in this field?
For me, I have been working in this area for my whole life. Okay, this is my career. Developed in corrosion science and engineering. I found it really interesting, and I'm glad and fortunate to be able to do something for the field. And for me, I think that to create next breakthrough. One thing is, first thing is, of course, we need to have develop a foundation and knowledge foundation, and also to more link up or communicate and talk with the industry, and to identify the key issues. Okay, and then continue working here. And the corrosion technology or corrosion science, compared to some other fields, maybe it looks like really a bit slow moving field. And for many industries, for example, oil and gas industry, you can see they are bit conservative in some way, I can say, because fair enough, because safety is really important. Okay, the industry really like to adopt a new technology. They really need to be testing and really careful analysis. But with because there's truly a need, then we talk to the industry, engage them, and working with them. Yeah, and then we would be able to make a contribution to the field. Just like AMPP, I'm specific. Really like to acknowledge the Materials Performance magazine. So what they are doing is truly is encouraging us and also younger generations really to encourage people to thinking to make new innovation and recognize it. So I really think the Materials Performance magazine and AMPP, this is a wonderful thing to do, and probably is one of the catalysts for future students and young engineers make a good contribution to the field.
So, Professor Tan, thank you again for joining us today, and congratulations once more on your team's achievement. We're excited to see how this technology continues to evolve and protect critical infrastructure in the years ahead. And to our listeners, thanks for tuning in to this special Materials Performance Innovation Awards edition of the AMP podcast. We'll be back soon with more stories from the front lines of innovation in corrosion and materials protection.